I would like to welcome everybody to our public lecture series. First of all, I would like to thank all of you for coming here. This is a great pleasure to see the interest in those lectures. And of course, for us, sorry?
Not very well.
You can, I think that this is pretty good. So we appreciate this. We love doing science. And of course, you are the ones who are funding it through your taxes. So obviously, this is a great thing. So welcome on this particularly important day today. As you know, Nobel Prize was awarded today to people who are doing work in astrophysics and cosmology. The Nobel Prize was given to people who are working on gravitational waves, and in fact, the detection of them was the reason for the prize. So let me introduce Zeesh Ahmed today, who is a research scientist at Stanford, and in fact, in particular, he's working at SLAC. Zeesh was an undergraduate student at University of Southern California and then went on to get his PhD at Caltech and came to work with us at Stanford as a postdoctoral fellow. As time went on, Zeesh was recognized as one of the leading people in his field and was awarded very prestigious Panofsky Fellowship, which is the fellowship awarded, only 2 of those every year, for people who are in the mid-career, who are continuing towards on a trajectory towards being very much leaders in a field. And in fact, was also recognized just very recently, a few months ago, that Zeesh's research is very much cutting edge, and he was given the Department of Energy's prestigious Early Career Award. Most of his work is on cosmic microwave background and various aspects of it. On one hand, Zeesh builds and deploys instruments in very interesting remote places around the world, but he's also one of the leading people who develops and understands the theory of the results of the observation. So without much more ado, let's welcome Zeesh here.
Okay, let's see, can you hear me? Great. Thank you, Greg, for that generous introduction. So hi, and welcome to SLAC. Today I'm excited to share with you a very intriguing story. So this is the story of the birth of the universe as seen through some of the most sophisticated cameras we've ever built, put into some of the strangest places on Earth to get images using these cameras. I guess figuring out how the universe started is one of the most profound questions we can ask. It's certainly a very compelling question for me. I'm very personally interested in it. And I'm excited to work on it. And so we'll be talking about the birth of the universe from these strange places, these remote places today. So my title slide, I should point out what's going on over here. So this is the Bicep 2 camera. It is located at the South Pole. So the geographic South Pole is about 1 kilometer in that direction from the point that this picture has been taken. And this picture has been taken at sunset. There's only one sunset per year at the South Pole. There's one sunrise and one sunset. And this is because of the tilt of the Earth. And most of Antarctica is either in the dark or in light for 6 months of the year. So this is as the sun is setting, and it's about to be nighttime and winter at the South Pole. The pattern you see up here, we'll be talking about this later, is the polarization pattern of the oldest light in the universe that comes to us straight from the Big Bang. And this is the kind of stuff that cameras like this try to image, and I'll be talking more about this. Okay, so the best way to give an overview of my talk is probably using this cartoon graphic over here that captures the story up front for everybody, and then we can break it down and go through it. So this is, on this horizontal axis over here is time. And if that's the start of the universe, t equals 0, or the starting time, we're here today, 13.8 billion years later. Okay? We're here on Earth. This is a satellite. This in particular, this graphic was made by the WMAP science team. So WMAP is the satellite, and so that's our satellite. And so satellites like this and cameras on Earth are observing our universe. And if we keep going back in time, we cross the various phases of development of the universe. Okay, so any slice through here is a slice in time of how things looked in the universe at that point in time. So today, we know the universe is accelerating, and in fact, the acceleration is speeding up. Okay, so that's actually another talk all in itself. The accelerated expansion of the universe. The regular expansion that happened over time is when galaxies and planets and clusters of galaxies and so forth formed. And if you go back far enough in time, you eventually come to the point about 400 million years after the start of the universe when stars were first switching on. Right before then, it was dark. There was nothing there. Or there was stuff there, it wasn't glowing. Stars hadn't turned on yet. And if you go back even further, you get to a point 380,000 years after the start of the universe. And this is the glow of the Big Bang, the afterglow of the Big Bang, and it's called the cosmic microwave background, or CMB. I'll use the word CMB quite a bit in this talk. And so this is the oldest light. We can't see farther than this, but we can see this point. Okay? And then we have an idea of what probably happened before then, and the stuff that happens right from point 0 up to this point. But this is one of the most interesting areas of research in CMB today. So we'll talk a bit about that. So that's the overview. Let's get started. So let me start with some basics. You all probably know this, but a reminder is always good. So light is a traveling and pulsating electromagnetic field. Okay, so if I were to draw a cartoon, this is what it would look like. A light ray travels in this direction, and the electric field is pulsating up and down like this. And the direction of this electric field going up and down is called the polarization. Okay, so here I'm showing light polarized in this direction, and here I'm showing light polarized in that direction. So straight like this, or like that. Okay. So this is important. Remember that we're talking about electromagnetic fields. There are waves, and the direction of the field is the polarization. Okay, so unpolarized light, or most of the light around us, is a mixture of various polarizations. But if you put it through a polarizing filter, like perhaps polarized sunglasses, then you pick out one polarization. Okay, and this is important because there are things in the universe that preferentially pick out polarizations. And this is why I'm telling you this. In general, whenever light bounces off electrons, there's some kind of polarization effect going on. Okay, so net polarization is what we care about over here. So if there's a preference of one polarization direction over others, right? Okay, let's look a bit more at waves. So this is the electromagnetic spectrum, and many of you are probably familiar with it. You can have everything over here, from radio waves to gamma rays, is basically light. Okay, the distance between two consecutive crests or troughs is called the wavelength. Okay, and the number of waves that pass a point at any given time per second is called the frequency. So these are two related concepts, wavelength and frequency. And really, really short wavelengths are very energetic. So gamma rays, we all have a sense, we've heard this, are super energetic, and their wavelengths are about the size of atomic nuclei. And you can go this way towards longer wavelengths and pass through X-rays, ultraviolet, visible, infrared, so forth, keep going, and the sizes of things characteristic of that wavelength keeps on increasing, okay? So what I'm saying is, as you get to these lengths of kilometers, radio waves are the size of buildings, right? And so somewhere in the middle over here, at these wavelengths or these frequencies, is the visible spectrum. This is what we see with our eyes. Okay, the next important point is that everything emits light of some wavelength based on its temperature. Okay? So if you're the sun and you're a few thousand degrees hot, you fall here on the spectrum, and then you go back up and you see where you fall on the spectrum and what wavelength of light you're emitting. So that's approximately visible. If you're a human being and you're about 98 Fahrenheit is your temperature, then you're somewhere over here, and you're more in the infrared, and that's why infrared goggles work really well to find people in the dark. And if you're really cold, you can be the temperature of the universe, and you emit in the microwave. That's the general principle over here. Let me point out the scale over here. This might be a funny unit to you. Kelvin, that is counting temperature from absolute 0 and up, okay? So it maps on fairly well to Celsius, in that 0 Kelvin is minus 273 Celsius, and then you just count upwards. So that temperature is about minus 460 Fahrenheit. And when you get to really high temperatures, it's about the same, right? 10 million Kelvin is about 10 million Celsius. The difference is just 273 degrees. So the point over here is, if you have a temperature for any object, then you know what wavelength it's approximately emitting in. Okay? Next concept. When objects that emit light move, their wavelength can change. Okay? So we're interested in stars and galaxies and things out as we look out into our universe up in the sky. And if those objects are moving away from us, their wavelength gets stretched and they appear redder. Okay? That's called a redshift. So if something's moving away from you and it's emitting some light, the wavelength gets stretched, it's redder, redshift. If it's coming towards you and emitting light, and you look at that light, the wavelength gets compressed and it goes towards the blue side of the spectrum. So let me go back over here. So what's happening over here is, if it's getting shorter, it's heading this way, which is bluer. And if it's getting longer, it's heading this way to the left, it's getting redder. So that's redshift and blue shift. Okay? This is important because of the next slide. So in the 1920s, Edwin Hubble noticed that galaxies in general seem to be receding from us. And the way he figured this out is because their wavelengths were redder than they ought to have been. And he also noticed that they're redder the farther away they are. So the farther away they are, the redder their wavelengths, the faster they're moving away from us. Okay? So after a few years of observation, by 1929, he concluded that the universe was expanding, because galaxies were moving away from us. The objects that were farther away were moving faster. What he guessed was that the universe is kind of like a balloon, and it's expanding. Okay? And so if this is the picture of the universe today, what he observed was, as things were moving apart, the universe is going to expand and become more like that in the future. And in the past, maybe it looked like that. Okay? So perhaps it was really small at some point in the past. Okay? So keep that in mind. Let's talk about light for a second, and this is interesting. It's worth a reminder that the speed of light is finite, and it's 300,000 kilometers per second. So interestingly, in our universe, given how big it is, that turns light into a time machine. What I mean by that is, when I look at the sun, it's 150 million kilometers away. We see it as it is 8 minutes old, because it's taken 8 minutes for that light to get here, right? So this image of the sun, when it was taken, was already 8 minutes old. Now, in this beautiful picture of the Milky Way galaxy, maybe some of you have seen this from a desert or something where there's not too much light pollution. The center of our galaxy is about 25,000 light years away. So that means we're seeing it as it was 25,000 years ago. Okay? Let's kick that up a notch. So this is our neighboring galaxy Andromeda, and it's 2.5 million light years away. So we're looking at it as it was 2.5 million years ago. And interestingly, if there are Andromedans over here, human-like people over here, or some intelligent life, looking back at us, they're looking at the Milky Way as the Milky Way was 2.5 million years ago. Okay? We didn't even exist. Our species did not exist at that time, when they were, if they're looking back at our galaxy today. So again, we can keep doing this. This is a cluster of galaxies called Abell 2744. It's 4 billion light years away. So this light is 4 billion years old. Same thing if they're looking at us, they're seeing us as we were 4 billion years ago. Let's keep pushing this. Hubble Ultra Deep Field. So this is one of the most sensitive optical images ever taken. This was done by the Hubble Space Telescope by pointing to a part of the sky that looked dark, like there was nothing there. And it's a very small part of the sky. It's actually smaller than the full moon in the sky. So it's about 1/10 of the size of the full moon in the sky. They added all these images together, and they found 10,000 galaxies. Okay, so a seemingly blank space and blank area of the sky, or empty area of the sky, and there were 10,000 galaxies over there, and the light from these objects is 13 billion years old. Okay? So, can we see all the way to the beginning? So I love this woodcut because it really captures what we're trying to do over here. Look back in the past, and see maybe we get to discover the workings of the universe. Okay, so the picture we have then is, as you keep looking back in time, so this is a cartoon of how light would appear to us based on where it's originating. So this is 13.7 or 13.8 billion years, which is the age of the universe, and that is 0 over there. And the idea is, if we keep looking farther and farther, we pass the Hubble deep field. I didn't show a picture of the deep field. I showed you a picture of the deep field. We're looking at the earliest galaxies in the universe, right, when the universe was only about 400 to 700 million years old. If we look past that, can we look past that? Can we get to the point where stars hadn't even ignited yet? Can we look past the dark ages and look at the very first radiation in the universe from the Big Bang itself? So this is a video version of exactly that graphic that I just showed you. So we're zooming out from Earth, and imagine you're now looking at Earth the farther and farther away you are from it, and so you're sort of looking back in time at us. So you're zooming past objects, the solar system. We're pretty soon going to zoom out of our galaxy. This is a video from the WMAP team again. So that's a cartoon representation of our galaxy, and we're going back farther and farther in time. So we're passing other galaxies now. These are perhaps some of the earliest galaxies in the universe. These are the first stars switching on, and then suddenly it's dark for a second. That was the dark ages. And eventually the idea is we should reach the hot, dense plasma of the early universe pulsating this way. And can we get an image of this? That's the question over here. And so it turns out that in '64, these guys accidentally discovered this. So in '64, Penzias and Wilson discovered the oldest light in the universe using this contraption over here. So it's a giant radio horn, and they were looking for reflections of microwave of balloons and test satellites. Okay, and they found a strange noise in their system. So the end of this horn is connected to an amplifier, just like a stereo amplifier, but it's an amplifier. It magnifies the radio signals, and they were looking at the signal. And this was a very sensitive setup. Their amplifier and sensor was cooled by liquid helium, okay, at 4 Kelvin, 4 degrees above absolute zero, to reduce its noise. And they picked up this noise that was about 3 Kelvin in temperature, okay, and they couldn't get rid of it. They got into the horn, scrubbed it clean, got rid of bird poo, and still could not get rid of this noise, okay? And so it turns out what they found was the glow of the early universe just redshifted down and now in the microwave, okay? So I'm going to show you in a second what an image of this might have looked like. So we don't have actual images for what we saw. But just to quickly orient you, the Earth is a sphere. I can flatten it out, and that's a flat projection, okay? And that's the equator as you would see it on a flat projection of our spherical Earth. I can do the same thing with the sky. So I can take the sphere of the sky, flatten it out, and this is the Milky Way. And what we've done is this is in galactic coordinates, meaning that the galactic plane has been put on the equator for this map. And so this is an optical wavelength, so you can see our galaxy and you can see stars and so forth. This is what these guys saw, basically. Okay, it was basically plain, completely uniform, with the exception of some of the microwave glow of our own galaxy. So this was about 1 millimeter wavelength, which corresponds to about 3 Kelvin in temperature. And so this is the cosmic microwave background. And what it is it's the glow of 3,000 Kelvin plasma early in the universe, but now extremely redshifted. Okay? And so this was emitted 380,000 years after the start of the universe. And over time, as the universe has expanded, that wavelength has gotten stretched, and it has moved from infrared, from visible and infrared, a red-hot universe, literally red-hot, and it is now in the microwave. Okay, so this is the oldest light we can see. We can't see past this point. The reason we can't see past this point, I'm going to use this gaudy graphic over here to explain. So we're showing the progression of time, and the only thing that's important over here on this plot in time is 380,000 years after the start of the universe. So this is the point we can look back to. Okay, so this is where the CMB, the cosmic microwave background, starts, and this is going forward in time. Before this time, the universe was hotter than 3,000 Kelvin, and so atoms weren't really atoms. Atoms were all ionized. There were nuclei, so we show over here some hydrogen and helium nuclei, which are basically protons and neutrons, but they weren't attached to electrons. It was too hot for them to be attached. So there were too many free-floating electrons out there. And when you have free-floating electrons, these yellow lines, or these yellow waves, show you light. Light keeps running into the electrons. Can't really go straight very far. So it's like a fog at that point. It's opaque. The light doesn't get very far before it gets caught by another electron. As the universe is cooling and the temperature drops below 3,000 Kelvin, which is that point 380,000 years after the start of the universe, that's when electrons can find the neutrons and protons and become neutral atoms for the first time. So now you have hydrogen and helium in their atomic form, neutral, and light can travel straight. And that light kept traveling straight and came to us today. So that's the general principle. This is why you can't see beyond this point. Okay, so let's get back to this. Here I've just removed the stuff from the galaxy, from the galactic plane. So this was what the microwave background was in the mid-60s. Okay? Then it took many, many years, a couple of decades in fact, to realize that there are actually small variations on this. So this is an image from the COBE satellite. COBE was a cosmic background explorer. And this was a satellite flown in the 90s. And they realized for the first time that there are slight perturbations or slight deviations from that 3 Kelvin. And actually what they determined was that the temperature was something like 2.72548, and the deviation, the variation was after that. Okay, so the deviations are 1 part in 100,000, which means that this is precise to the first 5 places of decimal, and then the number changes. So the color variation that I'm showing over here is a part in 100,000. So very, very tiny variations. So there were more missions, more satellite missions. There were a lot of ground-based cameras. They continued refining this picture. So I've been showing you full sky maps. Eventually we'll get to sectional maps made by ground-based cameras. But over the next 20 years, we go from COBE to WMAP, the Wilkinson Microwave Anisotropy Probe, and they refined that picture a little bit more. The deviations didn't go away. They were just found with more signal to noise, or the cameras were more sensitive, and they kept seeing that the temperature was uniform, and these little spots were really changes in the 6th place of decimal. Okay? Go another step. This is the Planck satellite, which imaged the CMB in the late 2000s. And so this is probably the best resolution and noise picture that we have of the full sky of CMB. Okay? So let's take a break for a second and look at how one actually takes sensitive pictures of the CMB light. And so the answer is, unfortunately, it's not as easy as with CCDs and with digital cameras. It's a little bit more complicated. So let's work a little bit through the history of that. So back in the day, they used microwave radiometers. So this is just the Bell Labs horn antenna that Penzias and Wilson used. So there's typically a horn, okay, and an amplifier. Okay, over here it's a room, and the amplifier has a room in there. The room has the amplifier in there. But this was common to a lot of the instruments back then. Even in the COBE receiver is the camera unit as of 1989, and WMAP in 2001. So you had horns connected to a low noise amplifier. So that's low noise amplifier in there, low noise amplifier in there, low noise amplifier in there, horn, horn, and a bunch of horns over here on both sides, actually. So it's hard to see the ones in the back. But through the 90s, so starting in the 60s and through the 90s, this was sort of the state of the art. You'd put horns pointed to the sky and connected to an amplifier. The revolution was actually this idea of a bolometer, okay? And this idea was actually is fairly old. It comes from the 40s, and it's really interesting because at that time they imagined the bolometer as something that sees warmth miles away, will help fight disease, warn of fire, catch burglars, spot heat leaks. So an idea probably ahead of its time, but the concept is basically if you have something that emits radiation, and we know everything does, with a sufficiently sensitive sensor, you would pick up that radiation, even at normal temperatures or low temperatures. And this was accomplished by putting the sensor at very, very cold temperatures, okay? So they have a can of liquid hydrogen in here and liquid nitrogen. So that's interesting. But they would be able to do this kind of imaging. So that was the concept. So let's break that down a bit further. So if you have incoming radiation or power, and it gets absorbed in something that is thermally isolated from a stable temperature, okay, so there's an insulator separating the absorber from a stable temperature, then you can stick a thermometer to that absorber, and if power comes in, it doesn't flow all the way, it doesn't flow into your stable cold temperature bath immediately if you've choked it a little bit, okay? This allows the temperature of the absorber to change. So if the power increases over here, the temperature goes up because all the heat has not immediately flowed into the cold temperature bath. I have a great analogy for this that I thought of the other day. So we're going to talk about this now. So my analogy is imagine a kitchen faucet, and the rate of that kitchen faucet and the water coming out of it is your flow or your power, and this kitchen sink is your absorber, okay? Your garbage disposal, if it's blocked or is choked a little bit, is your insulator over here, okay? Obviously, in our lives, we don't want our garbage disposal to be choked. But if you choke it a little bit and you back up water over here, then you collect some water over there, and the amount of water over there is telling you what that incoming power was, okay? So that's the general concept of a bolometer. Bolometers in the 90s look like this. So this was made at Berkeley. This is this contraption. That's 1 centimeter for scale. It was a little sheet of sapphire. So this gray thing is a sapphire over here, suspended by thin wires. Okay, so that creates that thermal isolation. And this is your thermometer. Okay, and so you'd have light fall on this thing, and it would change the temperature of this very, very sensitive thermometer. And a typical bolometer camera, as opposed to one of those microwave radiometers, would then have a few of these sensors, and you would look at the sky. Okay, so that's in the early 90s. Then this beauty came along. So this is a micro-machined bolometer. So that's a dime for comparison. This was made at JPL. So let me talk about that on the next slide. Over here, the idea is that they've used photolithography to etch silicon and create these thin legs that are that isolation. Okay, so heat gets picked up over here if light comes in over here onto this spot, and so that light focusing, by the way, is done by horns in this case, and this is exactly the sensor that was used for Planck, the Planck satellite. So light gets collected over here, and then heat flows through over here, and the temperature of this guy is changing as that power is varying on the sky, okay? So as I'm looking at different spots in the sky, there's very, very tiny differences in the temperature. I just said it was about a part in 100,000. So this thing is sensitive enough to pick up a part in 100,000 variations, all right? And so then a typical camera consisted of about 10 to 50 of these sensors. Okay, so let's get back to dissecting these images a little bit more. Okay, so I've shown you a bit about the camera technology at that time. Then we made these images. This is an image from the Planck satellite. Now, to make sense of this, what scientists like to do is to break up this image by scale. Okay, so there's variations, and remember these variations are a part in 100,000. So this is a very, very sensitive measurement. You can look at big spots on the sky, or you can look at tiny spots in the sky, okay? And what you could do is you could look at all the sizes in between. So if I were to divide up the sky into just 2 spots, what that would look like, or if I were to divide up the sky into many, many, many spots, what that would look like. And so I can take that image and figure out what the contribution of these various components is. So maybe it's a little bit of this, plus a little bit of that, maybe none of that, but more of that. So I can do this, okay? So you can do this exercise, and this goes on for a few thousand spots. You can do it as much as you want, all right? If I do that, then I can make a graph like this. And what's going on in this graph is, on the left end is big scales in the sky, so fewer spots. So maybe there's like 1, 2, 3 spots in this image. And on the right end, I'm going through to more and more spots. So you can see the scale or the number of spots roughly over here. And then I'm turning up or turning down the contrast on that scale of spots. So what this breakdown tells me is that the contrast on the large scale is not that much, but the contrast on this particular scale is really, really good, is really high. So the deviation from that average, okay, the deviation from the average on this size spot is quite a bit higher than the deviation from the average at this or perhaps at that. Okay? So what does this tell us? So this is really interesting. Immediately you can tell that there's some structure over here. Okay? And this is the most amazing part. So this tells you what the most prominent spot is on the spot sizes in the sky, and this corresponds to the most prominent size of plasma fluctuation or plasma wobbling in that early universe, in that image that I showed you, in that video that you saw earlier where you saw the plasma pulsating, okay? So this is the fundamental note of our universe at the time of the CMB. And so for folks, so for music enthusiasts, this corresponds to, let's say, the fundamental note of the universe if it were a musical instrument. And then the rest of this is harmonics. So it turns out that if you study the fundamental note and the harmonics, you can reconstruct all kinds of things about the universe. This tells you the geometry of the universe. The ratio of the heights of these peaks tells you other stuff, like how much stuff there is in the universe, how much matter, how much dark matter, and so forth. And this is why studying this very early image of the universe tells you so much about the universe, and it's so important in cosmology. Okay? So that was a cartoon representation. This is actually this is the real. This is what our universe looks like. This tells you a lot of things about our universe. This model is fit by data really well. So all the pluses and lines over here are data from these various instruments. That's the Planck satellite, and then the rest of these are cameras on Earth. The plus tells you the amount of uncertainty, and you can see that the error bars, the uncertainty from the Planck satellite is very, very tight, actually. It almost disappears into the line over here, okay, all the way down to many, many harmonics. And it starts blowing up over here because then the satellite dish is not big enough to get sufficient resolution beyond that point. That's where the systems on Earth help us out a bit more. But so we understand this really well. We have the data. It fits this curve really, really well. Okay, so we understand the story of the universe as seen through the CMB. Okay, let's go back to one fundamental question, though. So we've kept saying this, the CMB is so uniform. It's so uniform. The deviations are 1 part in 100,000. Why are the deviations so small? Okay, why did the CMB not look more like this? Okay, why not more like this and millions of degrees variation? Okay, so there's no reason this shouldn't happen. The way we explain this is inflation. So this is now where we talk about what happens before the CMB, and in particular this point over here. So what inflation does is, shortly after the start of the universe, in a very, very tiny split fraction of a second, the universe expands 10 to the 26 times. That's 1 followed by 26 zeros, okay, in a very, very short amount of time, 10 to the negative 32. 0.31 zeros and then a 1, okay? So very, very voluminous expansion in a very short amount of time. And what it does is it inflates a subatomic volume, something very tiny, to very, very large scales. Okay, why does that help? How does that help with the problem? So if my universe were something like this shortly after the Big Bang, and then the universe expands maybe somewhere in this orange patch very quickly, then the whole thing becomes orange. Very simple idea in principle, okay? If that sort of very rapid expansion happens, then suddenly everything has become uniform. Inflation stretches out space and removes all of the unevenness, except for the stuff that was uneven at subatomic or quantum scales, okay? And so that perhaps explains why you have these tiny variations. So let me expound on that a bit more. Inflation expands subatomic unevenness into lumpiness in that early hot plasma, that video that we saw, okay? So all of that lumpiness came from subatomic unevenness being magnified by this idea of inflation, okay? So some spots end up being more dense, some are less dense, and therefore some are more hot and some are less hot, okay? And so that's how you end up with these spots. And the most important thing is inflation is one of the only known mechanisms is one of the only mechanisms that we can think of that provides just the right amount of lumpiness so that these dense parts eventually contract under gravity and become our stars and galaxies and clusters of galaxies and all the structure we see in the universe. So if you don't have this, then the unevenness is too big. You don't get the right amount of stuff condensing and becoming stars and galaxies and structures of galaxies. Inflation, by magnifying the subatomic stuff, gives you the right scale. The 1 part in 100,000 is what you need to start off the process of creating stars, galaxies, and structures in the universe. So that's why inflation is cool, and it explains, it's a good explanation for how the universe started, or what happened immediately after the Big Bang. So now we've proposed this, but can we look back farther than the CMB and see inflation? Turns out not directly, because as I said, the universe is opaque, but there is a way. So here's another cartoon of the story of our universe, and this time we magnify the parts before the CMB. So in the other one, you saw all the structure formation and the dark ages and all that kind of stuff. This is the modern universe, this is where we are today, and this is the moment of Big Bang. It turns out we don't need to worry about this for the purposes of our talk today, but let me point out that this is the cosmic microwave background. So going forward, this is the CMB light at 380,000 years. And the idea is that if inflation occurred and it magnified the subatomic unevenness into the lumpiness in the plasma, which over here the technical term is density waves, but this just means unevenness in the plasma, or lumpiness in the plasma. If inflation did that, then the other thing inflation would have done is stretched and squeezed space-time itself and created gravitational waves in it, okay? So we just heard, and maybe many of you heard today, that the Nobel Prize for Physics this year was awarded for the discovery of gravitational waves. That was gravitational waves generated by colliding black holes, okay? We're saying over here that these gravitational waves are created by inflation. They're not fundamentally different types. I mean, anytime you move matter around, by shaking my fist over here, I'm generating gravitational waves. It's just that they're really weak, and LIGO detects them from cataclysmic events like colliding black holes. Here, the cataclysmic event that occurred was in the very early universe, and it created a lot of gravitational waves. They're too weak to directly observe today, so LIGO can't pick them up. What we're counting on is the gravitational waves that are generated by inflation imprint themselves in the CMB itself, okay? So we can't see past it, but if gravitational waves went through, then maybe they imprinted the CMB, with polarization, this is where polarization becomes important. The imprintation occurs in polarization of the light. And we look for a particular pattern called a B-mode pattern. And I'll come to that in a second. So remember this B-mode polarization pattern in CMB imprinted by inflation is how you look for inflation. Okay? So let's continue the story then. Okay, now I threw polarization into this, and now I need to go take pictures of polarized CMB as well. Just temperature pictures is not enough. Just intensity is not enough. I need to look at polarized CMB. So how do we do that? We become clever with how to make bolometers, and really you need some grids or something, right? I mean, we talked about this idea of polarizers or picking out polarization being related to a polarizing grid. And so you could put two grids like that together, perpendicular. This is a 5 millimeter polarization sensitive bolometer in which you see both parts of the grid. What they do is they fabricate this, and then they metallize only one axis for one polarization, and they take another piece and they metallize the other direction for the other polarization. So then you stick this behind a horn again, and then you get another camera. Again, the temperature, the bolometer part of it is there's a sensitive thermometer that's looking at temperature changes. And so this was used in BICEP 1 and also in Planck. So the thing that I didn't tell you earlier is Planck not only had spiderweb bolometers, but the JPL guys managed to get this onto the Planck mission as well. So that's Planck, that's the camera, and there are a few horns in here that do have polarization-sensitive bolometers. So now you can look at polarization of the CMB as well. The real amazing breakthrough came around 2008 when they figured out how to do all of this stuff, the printing of the polarizing grids, and they combined it with antennas. So these are now antennas, and they eliminated horns. So it's a one-step process where they've made this grid of polarization-sensitive antennas, and it all sits on one silicon wafer, and you put a few of those together, and suddenly you have 500 sensors as opposed to the 10s or 20s or 50s that you had earlier. So now you have antenna-coupled polarization-sensitive bolometers. The thermometers have become more sensitive too, and suddenly you can go up to 500 sensors in a camera. In fact, that wasn't it. This technology is still in use today. Probably the most sensitive 95 gigahertz camera on the planet is this one over here that we built at SLAC. This was SLAC's first CMB camera. It has 2,500 sensors. It's called BICEP 3, and we deployed it in 2015. This is an image in 2016. And so you see the squares again. There are 20 of those square tiles. They're about 3 inches across, and they have a few hundred sensors each. Okay, let me show you a few other cameras. So I already told you about the BICEP series of cameras. That's what they look like. This is a telescope called CLASS. So these are cameras that look straight at the sky without any radio dishes. Okay, so there are a few of these. Then there are others where the camera, so these are a few different types of cameras for, this is called the Simons Array. That's ACT, or the Atacama Cosmology Telescope, the 10-meter South Pole Telescope. This uses actually little tiny lenses on top of each of the sensors. These use horns still, instead of using the antennas. But here, these cameras are connected to a radio dish, and that radio dish looks at the sky, okay? So the camera, for instance, for this guy sits over here, in here. So light comes in, reflects, goes to a secondary, and then it goes into the camera, okay? So those are the cameras that take images of polarized light, polarized CMB light. So now we can say, okay, let's get back to the question of what does it actually look like, and what can we learn from it? All right, so now what I'm going to do is take that CMB sky again. So you guys have seen this image many times. We've cut out a chunk of it, a small section of it, in particular because I'm using BICEP camera images, and BICEP images a small fraction of the sky. So it focuses all its observing power onto a couple of percent of sky instead of the whole sky. And that's what polarization looks like. Remember, I said that it's basically the orientation of the electric field. And so that image, and you see lines in here, and the length of the line tells you the strength. And note that this says 1.7 microkelvin. So that's 1.7 millionths of a degree. So that is even more sensitive, or it's a lower number than the 1 in 100,000 fluctuation we were talking about. So cameras have had to get this sensitive to be able to pick out this polarization. The way this image, by the way, gets built is because you have slots like this, as you saw on the camera, so the images come out as pluses and crosses, okay? So the pluses and crosses combine to make that image. But what is interesting for us to find inflation is not to break it into pluses and crosses, but instead to break it into this mathematical combination of what are called E modes and B modes, okay? E modes are circular and radial patterns, and B modes are swirly patterns, okay? So look for those patterns, basically. So you can see some roundness over here, some radiative patterns over here. And in a bicep 2 image, there's hardly any B mode signal, okay? So you have to magnify it quite a bit to find it. And so if you zoom in and go to, what is that, 0.3 microkelvin, so 0.3 millionths of a Kelvin, or degrees above absolute zero, then you get something like that, and now you see some of the swirly pattern, okay? The key is that lots of stuff in the universe generates E mode polarization. So as that light has traveled from the beginning of the universe to us, lots of stuff has caused E mode polarization. There are very few things that cause B mode polarization, and inflation is one of them, okay? But this doesn't mean we've seen inflation. So this particular B mode is actually caused by our own Milky Way. There's stuff in our own galaxy that's radiating, and it's radiating some B mode. So we have to be careful about this. So if we're looking for inflation, we have to look specifically for the B modes that are generated by inflation and not stuff that comes from our galaxy. And the way we get to that is, remember this scheme again? You take the image, you slice it up into its components by size, and then you get something like that. So this is for temperature. And you can do the same thing for E modes and B modes. And this is what it looks like. So again, on the x-axis, I'm talking about going from large scales to small scales, okay? And this is, again, deviation from average. This is what you've been seeing earlier, and I showed you data on top of that earlier, so that's CMB temperature. But the moment I start looking at polarization, it drops quite a bit. The signal is a lot weaker. So E mode polarization is only about 10% of this, and B mode polarization is only 10% of that. So lots of E mode polarization still for our sensitive cameras. The B mode is rarer, and it's caused by a few different things, and we need to pick out the right thing. So it's caused by just structure in the universe. Okay, we're going to ignore that. I'm not going to go into much detail over there. There's some stuff from the Milky Way that we just imaged. And on top of that, we're looking for this slight hump over here, and that's the inflation B mode. So if this shows up, and we don't know the actual level of this, so this curve could sit over here. It could sit a little bit lower, but this is what we're after. So if we make those images, sort them into this big to small scale, and draw these plots, if something shows up over here, that's the inflation signal we're looking for. Okay? This is that same image with lots of data on top of it. And we don't have to worry about the details over here, except to show that you've seen that there's a bunch of data for temperature, there's a bunch of data for E modes, and notice how the plus signs are getting bigger, and that's because the uncertainties are increasing, because it requires that much more sensitivity to get to these smaller and smaller deviations from the average. Okay, so this is B mode, and this is B mode from structure, and remember what I said, we would see a signal over here if we saw inflation. So we need to get really sensitive in this area. So cameras that we build, we want them to be really sensitive over here. Here's yet another plot, and I'm going to show this only to point out one thing, which is this is again theory curves. This is what one model of inflation might look like, and if it's suppressed a little bit, then this is what another model of inflation might look like. The data is starting to hone in over here. And a few years ago, you might have heard the story of how bicep 2 potentially saw a signal over here. So bicep 2 thought that it found the signal over here. But it turns out that dust in the Milky Way accounts for most of it. And so when you remove that dust, these points move up a little bit. And this just says that it's an upper limit, which means we don't actually know what's going on over here just yet. And because it was showing up in the right place, that's why Bicep 2 thought that maybe they had seen a signal. But it turns out we have to dig deeper. We have to dig deeper, and we have to sort through all this mess over here. We have to sort through dust within our own Milky Way, be able to separate all these contributions to B modes. And to do that, we need more powerful and multi-color cameras. It turns out the trick to distinguish these things is color. So I can't look in just one frequency. I need to look in multiple frequencies. So basically, all I've told you right now is black and white technology, and we need to get to this color technology. We have it in the field now, but we need bigger cameras, multicolor cameras, to find this inflation B mode. OK, so in the last little bit of the talk, let me finally take you through the places that people go to take pictures of the CMB. So there's obviously space. Most of the images that I've shown in this talk are maps that have come from satellites in space. So it's been very successful. There's been COBE, WMAP, Planck. This is a video from the Planck science team. And they're not beaming out light, by the way. This is just showing you that this is how they scan the sky. Okay? So this is their scan pattern. And so it rotates. It maps out the whole sky, the sphere of the sky. And as soon as that is done, you'll see how the sphere then gets flattened out into the sort of image that I've been showing you. Okay, so that's where that comes from. So you get full sky images. The problem, of course, it takes a while to put together a space mission. Lots of money. Can't make it too big because you have to have it fit on a satellite. And typically, it's older camera technology. It takes about 10, 15 years to put together a satellite mission. Okay, but still, an excellent way. And then if we were to see any hints of inflation from Earth, we would put together a satellite mission to go after it. Another way is somewhere in between, which is ballooning. So that's a boomerang balloon. This is a spider camera. And so you could image the CMB from the edge of space. So put a camera on a balloon, get it just high enough to clear the atmosphere, get to the edge of space. This is an actual GoPro image from this camera. GoPro strapped to this took that, and there's a full video that goes with it, actually. And what you can do with this is you can't map the full sky. You map some fraction of the sky, about 10% of the sky. You can fly newer cameras because you grab a new camera, put it on there, fly it for a month, and it comes back down. But typically, the lifetime of these balloons is about a month. Okay, and then same over here, weight constraints. So the ground program has taken off and is very successful. And if you want to do this in the ground, you go to a high, dry desert. Okay? And that's basically to minimize seeing through water vapor in the atmosphere. Remember, we're looking for microwave. Water absorbs microwave. That's how your microwave oven works. So we want to minimize the amount of atmosphere we're seeing through so that we can avoid water vapor. So high, dry deserts. One of the most popular sites for running CMB cameras is in the Atacama Desert in Chile. So this is one particular site. This is Cerro Toco. This entire setup is called the Simons Observatory, and there are a few different telescopes over here. And this site is great because, one, it's extremely dry. So over here, you're seeing it in the wet season, but otherwise, it's very, very low water vapor. And it's high altitude. Oh, and I think, so this is closer to 17,000 feet. So very high altitude, so minimizing the amount of atmosphere you're looking through, and extremely dry, so less water vapor. So this is a fun drone shot video of this site. So that's the ACT telescope. And so I haven't yet been to this site, though I'm now participating in a project for which I hopefully will get to go over here. So getting here is pretty interesting. So you fly from here to Santiago, then you fly from Santiago to Calama. From Calama, you drive to San Pedro, and so that drive is about an hour. And then there's another couple of hours. And San Pedro is at about 8,000 feet. And then the rest of the way up to 17,000 feet, you drive on a daily basis. So you go in the morning, come back in the evening. Okay? And you go over a highway that connects to Bolivia, but right before entering Bolivia, you turn left. That's what I've been told. and you go up this dirt road, and you get to this wonderful site. This thing is called a ground shield, by the way, the structure around the telescope, and that's so that you don't have a direct line of sight to the mountains around you. Okay, so this thing is on Saratoga. It's a very tall mountain, but you don't want to directly see mountains as you're looking up. You don't want any rays of light coming off of mountains and entering your setup, so then you have something like that. Okay, so that's this wonderful site, and that's a Simon's array. So these are smaller telescopes, but also CMB polarization imaging telescopes. Then the other great site for CMB observations from Earth is the South Pole. So that's at 10,000 feet, lower altitude, but Antarctica is the driest desert on the planet. So desert, not sand, dry. Okay, so we want to go to the driest places. It doesn't matter if there's sand there or not. So let's see, over here, extremely dry. This is even better water vapor conditions than Atacama. High altitude, so minimizing the atmosphere. And the other advantage, of course, is there's one really long night. So you can keep observing continuously. Okay? All right, so now I'm going to walk you through the bicep story. So this is a story of this gang of people from all these institutions over here, including Stanford and SLAC, and our cameras. In particular, this is the Keck camera, and this is how it observes. So this is a video that's been sped up, and you lock onto one spot in the sky and continuously keep scanning across it. This is not like a digital camera where you take an image and you're done. You continuously keep making images and keep adding them on top of each other for years. Okay? So basically, cameras like this continuously scan. They take breaks for calibration, so that was a calibration right over there, and then they'll continue doing their thing. They just keep scanning the same patch of sky. So we've picked out that couple percent patch of sky that I showed you earlier, and it just does that. And as data comes in, this is what it looks like. So let me quickly orient you as to what's going on over here. So a few maps are going to show up over here. And this graph over here tells you as a function of time. So this is going from 2012 to 2016. As various cameras switch on and their sensitivity starts getting better and better as they're observing, you'll see the map quality get better. And this is not a E-B map, E mode, B mode map. This is a plus map. So you'll see the plus pattern develop over here. So that camera is kicking in its first noise, but very slowly you're seeing pluses starting to develop over there. Okay, so that's polarization. We use a grayscale map over here, and I know I've used many different color scales in this talk, but our team uses black and white. This is another camera switching on at a different color or different frequency. So this is our multicolor program now, and this is the third one switching on, and first noisy, but as time goes on, the pluses all start showing up. Okay. Let's go to the South Pole. This is how you go there. So we start in Christchurch in New Zealand. So fly commercial to there. And then you take one of these LC-130s or a C-17, and you fly to Antarctica. You first go to McMurdo Station, which is at the edge of the continent, and there's a few landing strips over there. One of them is actually out here to the right a little bit. And this is sea ice. It melts in the summer. So that's amazing. They can land the plane early enough in the summer, but then that entire runway just disappears. It just melts away. That's Scott's Hut. So this is what Robert Scott used as one of his storage locations starting his Antarctic expedition in 1911. So that's a preserved site now. You take another flight from there, again on an LC-130, and fly over most of Antarctica to get to the South Pole. So this is going over the Transantarctic Mountains, and then eventually you get to the South Pole. It's flat out there. There's nothing. There's quite literally nothing there. And it's hard to tell in this picture. It's kind of disorienting, but that's the horizon. And this is all ice. And it's 2 miles of ice. It's 2 miles high, so that entire altitude is ice, actually, sitting on top of bedrock. So that's the geographic South Pole is somewhere over there. This is the station. This is all the spread of the station. That's the skiway on which planes land. Here's where the CMB telescopes are. And you might have heard of a neutrino observatory called IceCube, and it's out there as well. Once you land, you're here. This is the Amundsen Scott South Pole Station. This is the actual South Pole, and you can pull this off without a face mask if it's minus 15, as opposed to minus 40. So cargo and people all come this way on these planes. So everything that's been built at the South Pole has sat in the belly of one of these planes. And these planes land on skis. So these are special LC-130s. They have skis to be able to land on ice. Here's our team, or part of our team in 2015. This might have been a member just having joined for that part of the season. That's the South Pole Station. It's an excellent NSF-run, National Science Foundation-run facility. Inside the station, it's nice and warm, 68 Fahrenheit. We have a control center for the telescopes. We have conference rooms, a dining hall, dorm rooms, so you can stay there. And of course, outside, a kilometer away from the station is where all the science activity occurs. So in this building over here is where the BICEP experiment lives. This is a new ground shield being put on for BICEP, so that structure that prevents other light from getting in. This is us working on the BICEP 3 camera, so those are the actual sensors, and this is the camera. Here's a cut through the camera, and it's like what you would imagine a camera to be. So there are sensors. So this is a cartoon of the sensors in that 4-tile version. This is the bigger version, and then there are 2 lenses, and they focus the light coming in. Okay, so like a regular camera, you put together this is just bigger and has fewer pixels. Okay, this is how you get the telescope up into its observing condition. It's a human-powered lift, and Roger O'Brien, well, I challenged Roger O'Brien to playing with a yo-yo while doing this lift, so that's that. Okay, and this is the finished product. So the title image was BICEP 2, then that's been replaced with BICEP 3, so it's a bigger camera. And this is reactions to the first light of BICEP 3. So I picked this off Google Photos, actually. If it sees a bunch of similar pictures, it turns it into a GIF. So I thought that would be entertaining. But this is us basically seeing the first light being captured and the first images coming in. A quick shout out to the people who stay behind after we install those cameras. So these are our winter-overs. So these are the folks who stay there overnight. It's only one night, right? For 6 months. Some of them grow long beards by the end of the by the end of the winter, but they stay over the winter and run our operations over there. Okay, I'm already a bit over, but let me quickly tell you what's coming up in the next decade. Bigger, more sensitive cameras, of course. So our bolometer technology is continuing to advance. We are now able to put multicolor capability into the same antenna and sensor. So that's really nice. And we've been able to make replicate a lot of sensors on bigger and bigger chunks of silicon. Okay? This is work done by our colleagues at Argonne National Lab. And this is all designed to basically go into cameras that have 10,000 or more sensors in them. And this particular thing has already been fielded. It's an SPT, which is our neighbor by BICEP. This is stuff we're doing over here and at NIST. So these are, again, same scale antennas, and we're trying to pack 2,000 multicolor sensors into these 15-centimeter silicon wafers that we can then tile edge to edge and build a big camera, okay? And so the idea over here, too, is that this is the technology. These kinds of sensors will go into future bigger cameras. And we're doing that because we don't want to stop with a small fraction of the sky. We want to survey as much of the sky as possible from Earth. And we want to match our surveys with some of the other prominent surveys that are going on. Some of you might have heard of LSST or DES. These are other optical surveys. And the structure that they see, we want to be able to match to the structure that we see in the CMB. So this is looking at much more recent stuff and matching it to stuff 13 billion years ago. So this would be a great step for everybody. This is, again, this is a different projection. This is a celestial projection, so that is the galactic plane. But this tells you very nicely the amount of sky that you can observe from different locations. So everything south of here is stuff that you see from the South Pole. This is stuff that you can see from Chile. And we can probably get to 40, 70% of the sky if we put something like 500,000 sensors on the sky. So that's what we want to do next. That project you might hear of in the next few years is called CMBS-4. You'll notice, of course, that there's a chunk missing over here. And of course, we want that too, because we're greedy. So a couple of other sites that we're interested in now. So there's Summit Station in Greenland. That's in the northern hemisphere, so maybe you can get to part of the sky there. And in the Himalayas, there's a site in Tibet that some folks are interested in. And so with those two additional sites, perhaps we can survey the entire sky from the ground. Okay, so I'm going to stop there by just saying the CMB has given us a wonderful glimpse into the very early universe. It's light that's coming from 380,000 years after the start of the universe. But there's quite a bit more to learn from it. Our cameras are getting more and more sophisticated, and over the next decade, we're hoping that we'll be able to understand events at the very, very start of the universe. So in particular, we want to image the effects of inflation and understand what happens this short fraction of a time after the Big Bang. So let me stop there. Thanks.
Sure. At this point, we're going to open the floor for questions. But before we start, I have to tell you that we have a very nice, sophisticated system which actually uses the microphones that are placed in front of you. If you are recognized by me, please, at that point, push the button in front of the microphone, and you can speak to the microphone. But when you're done, you should turn it off so somebody else can use it. So maybe I can start with the gentleman here who raised his hand first.
Okay, so this is working. One term I've heard regarding the early universe is reionization. Can you comment on where that fits into what you've talked about tonight?
Right, so, oh man, okay, I gotta show you that image too in a second. But here, let me go back to one of these. Okay. So there's a dark ages, which is when all the stuff in the universe is neutral. So it's neutral hydrogen, neutral helium. And that happens because the universe has become cool enough now that the electrons and nuclei don't live separately anymore. They become neutral atoms. When the first stars switch on, it is believed that they start reionizing all that medium, all that hydrogen and helium. So that's somewhere around here, that reionization kicks in. And then the medium becomes ionized for the rest of time, yeah.
So can we see light from the reionization period?
Right, so there is actually CMB signals we could see from the reionization period. There are actually many different ways of getting to reionization. One of them is that neutral hydrogen has a spectral emission at 21 centimeters. So the wavelength is 21 centimeters. And so that 21 centimeter ought to start disappearing as reionization occurs. And so one hope is that you could actually see reionized bubbles popping up if you image the sky in 21 centimeter. With CMB, at the very largest scales, CMB light is scattering off these electrons that are now, coming about.
So reionization is not uniform, it's bubbles here and there in different places.
Right, it takes time, yeah. And so it starts with smaller bubbles, that's what we believe right now, and that those bubbles get bigger and bigger until they all combine, and it becomes all reionized.
Thank you.
Hey, gentleman here.
The fact that you scan the same point over and over again suggests that it's static. Why isn't it constantly changing? Why isn't the image constantly changing of the?
Oh, great. That's a great question. Why isn't the image constantly changing? So two parts to that. The actual CMB is not changing. because the point at which that light gets released, it captures the state of the plasma right there and then. So the plasma was pulsating at the time, and when that light gets released off it, you've taken a snapshot of it. So that particular image is not changing. That instant in time is not changing, so that picture that we're trying to make is not actually changing. What is changing is the atmosphere right above us. And so that's adding noise. And by taking multiple images over and over again and adding them up on top of each other, we're suppressing the variation in the atmosphere that averages out. We say that it averages out by repetitive addition of the images on top of each other. And what you're left with is that static image back there.
Sorry, I don't understand at all why it isn't changing. You said it caught it in a moment in time, but the moment in time is a little bit later, is a different moment in time. This is coming at you continuously, right?
Yeah, that's right. So, there's another part of it here, which is the farthest out we can see is this point, this light, and as the universe continues expanding, it turns out that will always be the farthest point we'll be able to see, and so we'll see it cool off. So it's changing in that the temperature is dropping over time, and that frequency is slowly redshifting. So yes, it is changing, but on the time scale in which we're taking the pictures, the change is really, really slow.
So we're always seeing one point in time.
Yeah, we're seeing one point in time for all practical purposes. 1,000 years from now, maybe the image changes slightly. Yeah, so that's right. So it is changing very, very slowly. For all practical purposes, it's static.
How do you differentiate between B modes from the Milky Way and B modes from the CMB?
That's a great question. So it turns out, let's see if I can just pull up something that's helpful here. Let me replay this video again, so this will be helpful. So it turns out, I guess I have to say, there we go. Okay. This particular color is sensitive to both CMB and stuff in the Milky Way. This color is more sensitive to CMB, and this color is more sensitive to dust in the galaxy, so the Milky Way. So the different colors are differently sensitive. Their sensitivity to the different components we're interested in is slightly different. So you can add and subtract images in the right combination and tease out the parts that are only CMB versus the parts that are only stuff from our galaxy. That's the general principle. And you can do this with not just 3 images, but with 8 different colors or 15 different colors. We believe that from Earth, with the cameras that we can build over the next decade, we can probably do this with 8 colors. With a satellite, we'd probably go up to 16, 20 colors if we wanted to really get very high resolution, if we needed to.
Hello, I just wanted to say I thought it was really fascinating that you're using cameras to photograph this, and then when you were looking at the universe and talking about the polarization, that's almost like a sensor on a camera giving you that data. It was just really interesting parallel. Thank you.
Thanks for that comment, yeah.
There's a question back there.
Looking at your cartoon history of the universe, it looks like there was a big deceleration after the inflation period. Is that true, or is that just the way you had to draw the cartoon?
Right, so let's go back to the cartoon. So the question is this a deceleration over here, right?
Yeah.
So that is inflation switching off. So inflation starts, and it happens very, very rapidly in a very short amount of time. Of course, if it doesn't stop, then we don't have a universe. And maybe there are some universes out there where inflation occurred and never stopped. Fortunately, we're in one where it did stop, and then it just continues coasting until dark energy kicks in and the expansion picks up again.
So you're saying that that's not actually a deceleration, but a cessation of acceleration?
Yes.
We have a question here.
Is there a cosmic neutrino background?
There is absolutely a cosmic neutrino background. So there's a cosmic neutrino background. There's probably a cosmic gravitational wave background. All these things from the very, very early universe that have survived into modern times, there's probably some kind of background. But it is also, but there are many things that the temperature of the universe is not high enough to sustain those things or sustain those processes. So anything that survived that early era has a cosmic background. There's a cosmic neutrino background. We're, I should say, probably on the verge of picking that up too with some of the more advanced neutrino instruments.
There's a question right here by the aisle. Maybe that we start with this. Go ahead. You have to push the button on here.
So you were saying that the polarization is caused by gravitational waves. So how exactly do gravitational waves polarize the light?
Right. So that's a subtle thing that I decided not to go into in this particular talk. And unfortunately, I don't think I have a supporting graphic. So maybe if you're interested, I can show you something offline from one of my other talks. But the general principle is, just like you create, so hot and cold spots in temperature are created by these density variations in the plasma, right? And that's actual stuff being either more dense or less dense. The idea is that some part of this can also be caused by the way gravitational waves act on stuff and how they twist space and time. And as photons or light is scattering off electrons that are caught in those dense, less dense areas, they get polarized. Regular plasma unevenness creates only E-mode polarization. And gravitational waves, the way they can twist and distort space-time, they can create both E-mode and B-mode. And the actual mechanics of how that B-mode gets created, I might have a picture I can show you offline. But, and also, folks, you should feel free to look this up. But the general principle is that gravitational waves can create effects which can cause both E-mode and B-mode polarization.
All right, we have time for one more question, perhaps. Or maybe both of you, so go ahead. We'll start with you.
How many orders of magnitude more sensitive would the laser interferometer have to be to directly detect the gravitational waves?
That's an excellent question. So there are a couple of pieces of it there. One is just sheer sensitivity, and the other is what frequency range they're sensitive to. So on Earth, they can probably not achieve the raw sensitivity or probably the frequency range, so they have to go into space. You might have heard of this concept called LISA, which is putting these gravitational wave interferometers out in space, you know, in a satellite triangle formation or something. Or so if you can do that, then there are a couple of other problems still. All the other gravitational wave signals that are going off from colliding black holes, colliding neutron stars, and all these kinds of things, it turns out, I believe this is correct, and you should feel free to look this up, but I think you actually have to end up subtracting every single known source, and then what you're left with might be the cosmic gravitational wave background.
All right, perhaps one more question over there, gentleman in the yellow shirt.
Yes, on the day that the CMV signal was generated throughout the universe, what was the approximate diameter of the universe, and was the distribution of matter homogeneous? And then what does that say about our physical location in the universe?
Right, so that's an excellent question. So the universe on the day the CMB was generated was 1,000 times smaller in one dimension, so 1 billion times smaller in volume than it is today. And the size today of the observable universe, again, we don't know how big the universe is. We can just say what stuff might have contacted light will ever contact light. That's about 45 billion light years. So that's the size today on one side. Make that 1,000 times smaller. That's the size of the universe on the day the CMB starts propagating.
Okay. So that would be more or less 4 or 5 billion light years. And how long ago did this happen?
This was, okay, so, yeah.
It sounds like we missed the event.
Yeah, so there are a few subtleties over here. This is where inflation becomes important. So inflation does this thing so that you don't have to extend this all the way back there. So if you didn't have inflation, then the universe doesn't become big enough in size for us to be able to observe this so uniformly and across such a big universe. That's the general principle. Because I know what you're saying. Basically, you'd have to extend back quite a bit longer. The age of the universe would have to be a lot longer for the scales and the size to make sense. This is where inflation saves you. That's another reason you need inflation.
So we're not near the edge of the universe. We're we're in the middle.
In general, the universe appears homogeneous and isotropic in all directions that we look in. Yeah. And so, for all practical purposes, we're at the center of our observable universe. And at the edge of that, those guys are at the center of their observable universe.
Perhaps at this point it would be wise for us to allow the camera people to go home, to pack up here. But we will still spend some time outside of the room, maybe for a few more minutes, if you have any pressing questions. We'll be very happy to answer those. So let's thank Zish again. And just before you depart, I wanted to mention that we're in planning status of establishing a sort of ongoing astrophysics and cosmology public talks. And the first one of those will be, I believe, 15th of November. But certainly watch the same place where we found information about the SLAC public lectures, and we'll post the information there. So once again, thank you very much for coming.